Okay, so now it takes us to design optimization. So now we know that we can add information to this model. Our hope is by providing as much information that we can add we can basically have a good understanding of the boundary conditions. And if we know what the credentials are and the objectives are of this particular project, we can then try to optimize it, right? Because we have introduced it in a parametric way, and we want to do this in different design development stages, right? That's where you have the LOD, for instance, level of development. That's the design development stage, okay? And in every design development stage, you would have a different type of opportunity for you to basically build this and optimize it from the feasibility to a detailed engineering, okay? So as an example of how you would be able to utilize this, you have your computational, basically, optimization problem on how you're going to be doing this, starting from visual programming, information modeling, wind, and then you basically do it as a loop, and you can introduce it as a optimization strategy. So for decision support, we are going to be talking about essentially the dome of visions that we briefly discussed last session. Essentially, it's a house that has a force field around it, right? This is built 3 times, I think. Actually, all 3 times have been demonstrated in Denmark. One of it is right now, if I'm not mistaken, in Stockholm, and the other one is in Aarhus, which I actually collected some data there as well and did some analysis to see, okay, how is this actually going to work? You know, is this going to support some of those aspects or not? And this is basically the point cloud associated with it. I did a full, let's say, each and every one of these red are actually a prism, and the prism shows the orientation of the camera that I took the photos. I also took point cloud data from this as well. In one basically visit, I did the external part, and another one, I actually did the internal part as well. So I want to do a few analysis to basically see what the merits of this type of design was. And this is just something that you can think about if you're looking at creative designs and you want to see actually what is going to be the final result. So one is, for instance, daylight factor. Daylight factor is basically, in a crude terminology, how much daylight your particular, let's say, element, your particular house is going to be taking. This is an architectural aspect. It's important. Why? Because if we can increase the amount of daylight that every room, let's say, has, what is going to happen? You're going to lose less electricity for lighting. It's just going to be better. So, for instance, this average daylight factor, if you have no, let's say, surrounding, which this surrounding has basically a shield, this is going to be some sort of epoxy or some other types of, let's say, polycarbonate or let's say, other means, depending upon how it is. I did the polycarbonate for the analysis, and then each and every one of these elements also has some sort of thickness, and it has some sort of absorption rate and so on and so forth. So in general, based on its location, it gets 66%. If you basically put this together inside some elements that is going to have particular similar, let's say, thicknesses of 24 by 30, you're going to get it dropped by 48%. The other one is going to be 40 by 30. This obviously is going to be dropped again, right? Because now the elements are a bit bigger, a bit thicker. You have less potentiality for daylight, and then you can take it from there. So what this analysis shows that whatever this element size is going to be, and whatever exterior, let's say, lighting, window or whatever transparent, let's say, material you're going to be using is going to impact at least one of these factors. Let's see how it's going to be doing with respect to the structure. So you would have to simulate the wind loads. These wind loads, dependent upon the different standards, if it's really of significance, you need to be able to build exactly what the wind profile is going to be. If it's not of significance, you can use code-based, basically, minimal, let's say, requirements. For this particular aspect, it's important for us to be able to do it because we really want to know if this round hemispherical shape is going to actually have any type of aerodynamic capabilities as well or not. Snow load, exactly the same. Based on whatever code you're going to be using and where your location is, this is going to change as well. I did the analysis for the National Building Code of Canada. Why? Because both wind and snow in some of those Arctic regions are of interest and importance. That's why we wanted to see, okay, if we have a situation where wind and snow is actually of interest, is this going to impact some aspects of our final design of the building? Is it going to save some material, so on and so forth? So far, we know that this is going to reduce the effective daylight that we're going to be getting for us. Then we have to perform the combined load, and this it depends on what it is. We know that there's not going to be any live load on top of this, but we need to design it for the dead load of the particular structure, which is quite low, depends upon obviously the material and how we're optimizing it. But it needs to be able to withstand the snow loads and the wind load. And these typical profiles are performed through wind tunnel experiments, by the way. So you typically do it with scaled models. You perform the wind profiles that you require so that you can identify how the load distribution is going to be based on the amount of let's say, speed and various different aspects. And then you would need to know if it's turbulent flow and so on and so forth. I'm not going to go into too much detail, laminar flow. And so each and every one of these aspects requires you to have good knowledge of the engineering and what is going into it in order for us to simulate it here. Then, if we look at it into the Canadian Arctic, if you perform combined load, that means that this particular structure has to hold wind, snow, and live and dead load. We're able to have the mass around 157, let's say, tons, and this includes various aspects from a complete facility that you can add to it, not just the structural. The other one, 79. This by itself means that if we can minimize as much as possible the amount of load, especially in locations where snow and wind are actually of considerable significance, this can reduce it. Why? Because when you have a design where you have a force field, that force field is going to be holding what? Your snow and your wind or whatever external load that is going to be provided, right? Yeah. So here we can actually have some sort of situation like this. What does this mean? That means that, well, there's some benefits to it, some shortcomings. There's a decision that needs to be taken under consideration. The other side of it is that we can actually optimize this dome as well, right? So we can optimize and minimize as much as possible the weight, because that also has to be added to the weight of material that is going to be used, because the first option is going to be, let's say, it's going to be a complete finished product. The other one requires both this and the other building, right? So that also needs to be added. So we have to basically code to see what arrangement of these nodes and how many of them is going to minimize our weight, and then take it from there. There we would be able to see, okay, if we do it through steel, we can get, let's say, the optimized volume to this much, and the total mass reduction, instead of that 50% that we talked about, is going to basically get to a different number here, right? Aluminum basically gives us the best mass reduction, and the optimized volume is not as good as steel, but is pretty good. The wood basically is not really doing well in terms of volume. And why these volumes matter is with respect to the daylight factor, as well as just your general opportunity to have more space. So in terms of architectural, when you have more space, you have more opportunities to, let's say, plan the space more accurately. I mean, for just this shell, it wouldn't matter significantly, but it's something to keep in mind when it's an order of magnitude more than what you would get with steel, just to have an idea. Okay, so you have a bunch of different results here. We know that the mass is going to reduce regardless of what material we're going to be using. So the material usage is slightly going to decrease. but we also have some other aspects to it, right? So now let's think about, okay, how can we make a decision on this? What material can we use? What would be the best option for this? What this means is that what we need is a bunch of numbers based on different analysis that we perform, and a bunch of objectives and criteria that we need to make this measurement and this decision from. Okay, so for example, we have the optimized volume, the total mass, have the embodied energy, CO2 effective, as well as cost. Let's take a look at these. Embodied energy, we talked about what the embodied energy is, right? Yeah, so we know what that is. The effective CO2 is similar as well. Here, for instance, as we discussed, aluminum has quite a bit of a larger embodied energy and embodied carbon because of the way the general raw material is extracted. That is significant in terms of embodied energy. Steel is a bit better, so you can see a bit better. And then the cost is dependent upon the market and the availability. And hopefully, if we have a true free economy, free market economy, this is going to be basically with respect to the market demands and supply, okay? So we want to minimize the space, basically the volume. We want to basically minimize we want to maximize the total mass reduction or minimize the mass. This is good for the delivery and various different aspects as well. We want to reduce the environmental aspects, so reduce the embodied energy, reduce the carbon, and then reduce the budget. So this doesn't have, let's say, a just, you know, random, and then what is also important is that what are these particular objectives and constraints? How are they ranked? Which one are more important than the others? Each and every one of these will provide us with a different response and a different strategy. So how can we solve this? Do we know, let's say if you want to buy a car and you have a bunch of, let's say, constraints, how do you solve it? How do you make a decision? Are there any strategies that any of you know? Well, that's definitely the case. And all of these aspects, including the car, falls into a more broader category of multi-criteria decision making. Okay, so these multi-criteria decision making, one of the ways that you can solve it is through a process called AHP. Are you guys familiar with AHP? Analytical Hierarchical Process. If you're not, well, you're in for a treat because we're going to be talking about it. So Mr. Saati basically came up with this analytical, basically hierarchical process, which provides different hierarchies of what it is that needs to be carried out and its interrelation to each other based on customer or consumer or clients' basic needs, or the team stakeholders' basic needs, based on the level 1, which is going to be essentially your constraints and criteria, and level 2, which is going to be your solutions or options that you have. So I want to choose between aluminum, steel, wood, and these are my criteria. How can I do that? So what AHP tells us is that we need some weighting strategies. Now I put all of these in a very consistent manner, but what you need to be able to do is to create a comparison matrix where this matrix doesn't necessarily need to be consistent. You can put it as, let's say, 1 to 10, and you can say which one is the best, which one is the worst. And then the other one would be basically, doesn't necessarily have to be the inverse of that. We would put a number there. Now, the reality of it is that some research shows that that is an easier way of us being able to basically rank order what these actual constraints together are. Meaning, how much better is, let's say, mass compared to, let's say, volume? You know, how much more important that is. And every consumer would have a different one, and then you can sum it up and average it and then take it from there. And then once you have that, you need to perform what we call an ion value decomposition, and you can get what we get in terms of your priority vector, which is going to be the ion vector corresponding to the ion values. Once you have that for each and every one of these criteria together, you would get basically by means of your factors, you also have to perform that as well. So for each and every one of these, what score aluminum, steel, and wood are getting. And this one is a bit less subjective. This one, you get it from the engineering analysis directly. This one, you get it from stakeholders and let's say stakeholder sessions, or you distribute, let's say, surveys to see which one is better and which one is worse. So if you want to buy a car, is aesthetic more important than, let's say, fuel efficiency, and so on and so forth. That's the whole idea. Again, you perform the priority vector. So you have two matrices that you need to be, well, one is a priority vector and one is going to be matrix, but is going to be basically a vector for each and every one of these factors. And then you perform a matrix multiplication between them. And using that, you would get your final score. So if you get basically these as your initial weights, more or less in terms of average, you would get wood as your best option. If you change it, for instance, here, your embodied energy and carbon are not so important, but your mass is really important, you would still get wood. If, let's say, the mass is really important and embodied energy and carbon are not important, you would get aluminum, for instance, in this case. Okay? So this is one way that you can make a decision on what would be the best alternative. This is if, again, we do it in a more, let's say, standardized, more traditional way, that we look at each and every one of the variables separately, and we try to optimize it separately. So for instance, when I optimized my structure, I didn't care about too much other aspects there, right? The only thing that I care about was that I want to minimize the weight. Now, what if I look at other aspects while I'm doing this as well, all together? And this is the more holistic multi-objective optimization, that we can perform the same task, but we just, if we model the problem correctly, we can actually perform all of these optimizations together, right? So one thing to keep in mind, that this weight is important. How we're rank ordering it is important. And last session, I talked about how we can utilize Monte Carlo simulation to be able to just say, okay, this, we know in this session, we can come to some consensus. We would never be able to come to the consensus that this is going to be 3. Okay, this is for sure, from my experience, is going to be very hard. But what we can get to a consensus is that our volume is, let's say, less important than, let's say, our mass, and so on and so forth. This is something that we can do, and then we can utilize random variables many times and then see which designs are going to come up and pop up more. And this is basically what we talked about the last time with the dome of vision. If I want to find the best decision variables, which is in this case what that particular perspective center changes and the length of each and every one of these, and we talked about how we're going to be utilizing this by means of basically creating a deltoid on the top and a planar surface, and then changing the lengths of that, and then back projecting it onto a hemisphere and see where those points are going to take us. This is a full parametric method that you would be able to build a let's say, geodesic dome. And this is how the Dome of Vision actually 3 was created, which I think is a very brilliant design, because geodesic domes are not simple to make or design. So there are strategies that can be implemented and employed to create it. But this is by far one of my favorite strategies that they have utilized in order to create something that basically replicates a geodesic dome. It's not actually a geodesic dome, but it replicates that. So here, for instance, what I also checked, this comes from a recently published or accepted paper of mine in Nature, and this basically were the decision variables, and these were the objectives or the constraints that we wanted to some minimize and some optimize or maximize. So embodied energy, embodied carbon, weight, volume, strain energy, we want to minimize this. Operation cost, we want to minimize it, but fundamental frequency, we want to maximize. This fundamental frequency is for earthquake. You last time you talked about. I actually double checked, and apparently I did it in the analysis. So, which is good, you know. But what we would get is now a set of utilizing various different types of strategies. One strategy that you can utilize is non-dominant genetic algorithm, which looks at every time, once it generates your solutions from your initial population that you provided to, and then the initial population is going to be your initial design that you get from the point cloud, right? That is going to be your initial, basically, constraints that you're going, or one of the initial populations is going to be that, right? So that you can build on top of that and get the best design from there. You don't want to completely give it free because you already have some initial design there. But what we want to get at the end is a better design than what we had initially, right? So this is what we call the Pareto front. These are basically the solutions that are not better than the other one. Basically, whatever we're changing here is going to make the one other objective from these 7 objectives that are not going, some of them are conflicting with each other, is going to change that, right? It's not going to be an absolute one final best result that you're going to be getting. So for instance, here we want to minimize the strain energy and we want to minimize the weight. Obviously, what is minimizing the weight is, or the strain energy is maximizing here the weight, right? And one way of looking at it is that this is the design that minimizes the weight. This is the design that is going to minimize the strain energy. Obviously, you have much more elements, and with that, you cannot get necessarily to the weight that you need there as well. So this is something to keep in mind. This is just with these 2 criteria and other criteria as well that are going to be there as well. Then what needs to happen, I talked to you about this, similar to an AHP. This time, instead of us grading these one by one and trying to create a consistent matrix, I'm not going to talk about what that really means, but what it means in terms of like what it means computationally, but what it means is that if you say that, let's say your weight is more important than your volume in one part of the matrix, the other part of it, is that basically consistent with the other one, right? Is the amount that weight is more important than volume, is it following the same, let's say, rate as it would with respect to the strain energy? That's what that means. So in terms of the consistency. And you cannot generally ensure that prior to it unless you have that intention in mind, because if you're just putting it together completely separately, you might not get the exact consistency, but we can calculate to see how consistent they are. This basically circumvents that. What it says is that, okay, we just come together in some sort of design charrette or some sort of stakeholder session. We come to the conclusion and we come to the decision on which one of these criteria are more important than the other one. Okay, we get embodied energy and carbon. This, I've seen it being very, within 10 minutes, you would be able to get a consensus there. It's not that hard to be able to make that, but to get a number there is going to be very, very hard because that's very subjective. Once you get this, what you would get at the end is a set of opportunities. Once you get your Pareto front solutions at the very end of your basically converged genetic algorithm, is that you can simulate these many, many times, let's say 1,000 times with different numbers. So every time you have 7 different, let's say, variables, you go random, let's say between 0 to 100, you randomly select 7 numbers, and then you rank order them, and then you find which one of these designs are the best design. And then, interestingly enough, because of these constraints and these parts, you would get designs that basically show more often, because we know that these basically criteria are satisfied more with respect to this particular design. So you can see, for instance, 43% of the time this design, 38% of the time this design, 15% and 2% this design. And these were of wood and these were of steel. And this time aluminum didn't even get the cut because embodied energy and embodied carbon became very important, and aluminum is not that good comparatively in terms of those aspects. Right? So we can make a decision based on the information that we have. If we do not model the problem correctly, if we cannot model the constraints correctly, we would have no chance of being able to even get to a place where we would have 4 designs instead of 120 designs here. And these 4 designs we know for a fact are better than our original initial design or initial point that we had. We cannot guarantee, this is also something that is important. One aspect is that we really cannot have one design that is the best, absolutely, because these are conflicting objective functions. However, also, because we're using genetic algorithm and evolutionary algorithms, we also cannot guarantee that this final result is going to be the best heuristic result that we're going to be getting. However, what we can know for a fact, if we get it from an initial starting point, is going to be better than that initial starting point. That by itself is important. Sometimes what I like to do is I like to utilize in the multi-objective, for the most part, genetic algorithm is very, we have either the decomposition-based genetic algorithms or the non-dominant genetic algorithms. But for the single objective ones, you can utilize a combination of these and decide which one is going to be the best final result for your problem. You can actually get this objectively with some analysis and some calculations. Okay? So, generative design. Now, with this, you have some, let's say, basic outcomes that you know for a fact, and you have some initial constraints. If you have an initial design that you're going to be starting from, that is going to be good because you know what you're optimizing. The idea generally, and this is not anywhere close where we're at, is to just provide the constraints that we want. Let's say I want a building that works. Not that loosely, but you get the gist of it. You don't have an initial, let's say, design, but you have a set of designs that basically can converge and get optimized, right? That's the whole idea. That would be the final, basically, level where we want to get in terms of genetic algorithm, genetic modeling and generative design. But for now, we have some initial constraints that we confine the project there because we do not have good enough information or initial designs to be able to train, let's say, some neural network that would provide us with some sort of final results, right? Similar to what ChatGPT is. ChatGPT became ChatGPT because we have all of these information and data that we've plugged into it so that it could actually now more creatively come up with new ways of stitching this information together, right? That's the whole idea there as well. And then we can optimize it. So strategies of optimization. Really, I like to categorize it in 3 different categories. And these are for, let's say, single objective optimizations that you can utilize, but you can pretty much extend it to multi-objective optimization as well. The first is, I call it closed form or linear optimization. And this is basically, you utilize the simple calculus. If you want a minimization of a function, you get the differentiation of it. If the derivative of it is going to be 0, and it is concave up, that means that the second derivative is positive, then it's going to be a minimum. Example of this, you have a function like this, and then you get the first derivative of it equal to 0, you get how it is, yeah? So your x is going to be minus 4 divided by 3. Once you get the second derivative of it, is going to be positive, so it's going to have a negative, so it's going to be minimum, that minus 4 divided by 3. Fitting line to endpoints, you can actually put it as an eigenvalue problem. Again, it could get linearized, even though, especially with orthogonal, let's say, distance-based ones, algebraically, it's not linear. We can, in vector format and in matrix format, we can actually make it linear as an eigenvalue problem. And then that would be the eigenvalue decomposition of your covariance matrix of the data points, and that would provide you with your line. So this is one way. This is going to be an absolute deterministic, and it's going to be closed form. You might get numerical errors here or there if your matrices are badly conditioned, but that is a separate situation. What that means is that every time that you're performing this, you're going to get the same results. The second one is iterative optimization, and this is when your objective function has a derivative, but that derivative is not, or the gradient is not going to be easily solved using closed form strategies. So it's not going to be linear or linearized. And this is one example of this, is my paper on ellipse fitting, which you can linearize it somehow, but it's not numerically stable and it's biased in some areas because the true objective function is nonlinear. So I had to solve it using a Levenberg-Marquet method, which is basically a correction to the Gauss-Newton so that it could actually get closer to the objective function a bit faster. This, again, these two are deterministic. What that means is that one is completely in closed form, you would be able to get the final result, like x is equal to minus 4 divided by 3. The other one has to go iteratively, and with some final, let's say, 10 to the power of minus 4 error there, which is acceptable for us, we can stop this iteration, right? Root finding is one of the other examples of this. If the root is, let's say, something that is nonlinear, you can utilize the Gauss or the gradient descent or the Gauss-Newton method to be able to get the final root of a problem. The gradient-free stochastic optimization is when you cannot get the gradient or the derivative of this function. So neither can you solve this function in closed form, nor can you even get it. So which direction are we going to go towards? Because if we know where we are based on, for instance, in terms of the iterative, you get an initial estimation. Based on that initial estimation, we go towards what is going to be basically making our gradient zero. So every time we're basically approximating it in a linear way, we're basically going towards it. And while it's going, if it's this way, we're going to go towards it this way. If it's this way, we're going towards it this way so that we can get to the bottom, okay? If we don't know that, then we have to utilize numerical methods. So we have to utilize many different initial constraints. For instance, in the case of genetic algorithm or particle swarm, we get, initial population there that we work towards it. For instance, the simulated annealing also adds an extra layer of, let's say, random variable that we just go left here, right here, and then we kind of try to find, they have a temperature function to be able to do that. So each and every one of them has a strategy on how we would be able to find where that gradient is going to go, okay? This is what's very important, and this is where AI and evolutionary algorithm can even have a chance of doing that. If anyone is solving these two with AI, they're basically, they're misusing a technology that can be utilized very simply, using existing method more effectively. You're basically making it more inaccurate by doing that. And I have an example here as well that I want you guys to basically work together to try to solve this. So this is we have a few minutes left. I would like to ask maybe another 10 minutes as well. Let's solve this together so that we have something to work towards for the next session. Given is that you have 1, 2, 3, 4, 5 different surfaces. Your total volume is fixed. This is supposed to be a building, by the way. The cost to build the sides is going to be $6 or euros per square meter for every side. But for the top or the bottom, which we only are going to be focusing on the top, is going to be $10 per square meter, right? Find the X that minimizes the cost of the material used on the structure's envelope. So the first step that you need to carry out is to build a function, right? This function needs to be a function of your dependent variable, which is X, right? And from that, you have to see what the function is and decide what strategy needs to be carried out in order to complete this. Let's see where we're going to get. I'll give you guys 10 minutes to work into groups. First, build the function, and then utilize basic calculus to be able to perform the minimization.